What gap in existing research does SAMBA aim to address?
SAMBA aims to address the gap in existing research by harmonizing the strengths of state space models, SSMs, and attention-based models to achieve unlimited sequence length extrapolation with linear time complexity. Existing models either suffer from quadratic computation complexity or limited context extrapolation ability. SAMBA combines SSMs with attention through layer-wise interleaving Mamba, sliding window attention, SWA, and SWIGLU to capture both time-dependent semantics and non-Markovian dependencies efficiently. By integrating the strengths of both SSMs and attention mechanisms, SAMBA offers a simple yet effective hybrid approach that outperforms strong open-source language models in various tasks. Previous works have explored hybridization strategies, but none have achieved unlimited length extrapolation with linear time complexity, which SAMBA successfully accomplishes.
How does the proposed method SAMBA work? Provide a step-by-step illustration.
SAMBA is a neural architecture that combines state space models, SSMs, with attention-based models to achieve unlimited sequence length extrapolation with linear time complexity. Here's a step-by-step illustration of how SAMBA works. 1. Mamba layers. SAMBA incorporates Mamba layers, which capture time-dependent semantics through recurrent structures. Mamba enables input-dependent gating for soft selection of input sequence elements. It expands input representations to a higher dimension, applies short convolution, SC, for signal smoothing, and calculates selective gates for input selection based on low-rank projections and soft plus activation. Recurrent inference in the selective SSM S6 is performed in an expanded state space to capture long-term dependencies. 2. Sliding window attention SWA layer. To address non-Markovian dependencies, SAMBA includes SWA layers operating on a sliding window size of 2048. SWA retrieves high-definition signals from short to middle-term history through efficient attention mechanisms, ensuring linear complexity with respect to sequence length. 3. Multilayer perceptron MLP layer. MLP layers in SAMBA provide nonlinear transformations and recall factual knowledge. SWIGLU is used for all models, with separate MLPs for different types of information captured by Mamba and SWA layers. 4. Hybridization strategy. SAMBA harmonizes Mamba's recurrent sequence structures with SWA's precise memory retrieval and MLP's nonlinear transformations. This hybrid approach allows SAMBA to excel in handling various language comprehension tasks by leveraging the strengths of both SSMs and attention mechanisms. 5. Parameter allocation. SAMBA optimally allocates parameters to attention layers, focusing on information retrieval, where a small number of attention heads are sufficient due to Mamba's ability to capture low-rank information. The architecture supports a smaller number of attention heads, enhancing optimization for small language models. 6. Efficiency and performance. SAMBA outperforms other linear recurrent models and attention-based architectures in terms of training throughput, perplexity, and downstream task performance. The architecture's specialization in attention distributions and input selection probabilities contributes to its impressive results in long context understanding and memory recall tasks. In summary, SAMBA's innovative hybridization of SSMs and attention mechanisms, coupled with efficient parameter allocation and specialized architectural design, enables it to achieve superior performance in language modeling tasks with unlimited length extrapolation and linear time complexity.
What are the benefits of using SAMBA compared to existing models such as transformers and state space models?
SAMBA offers several benefits compared to existing models such as transformers and state space models. Firstly, SAMBA harmonizes the strengths of state space models, SSMs, and attention-based models, providing unlimited sequence length extrapolation with linear time complexity. This allows SAMBA to capture both long-term dependencies efficiently and model complex, non-Markovian dependencies effectively. Secondly, SAMBA outperforms strong open-source language models with up to 8 billion parameters on various benchmarks, showcasing its superior empirical performance. Additionally, SAMBA can be extrapolated to 1 million length in zero shot with improved perplexity on proof pile, demonstrating its ability to handle long sequences seamlessly. SAMBA also excels in memory recall tasks, surpassing SWA-based models in recalling memories beyond 4K length. Furthermore, SAMBA achieves significantly better performance on downstream long context summarization tasks while maintaining impressive performance on short context benchmarks. Lastly, SAMBA's hitectural design is validated through rigorous analyses and ablation studies, elucidating the mechanisms behind its effectiveness. Overall, SAMBA's hybrid approach combines the strengths of SSMs and attention mechanisms, leading to superior performance in handling long sequences and memory recall tasks compared to existing models like transformers and SSMs.
How was the method validated or tested in the paper?
The method in the paper was validated and tested through a series of experiments and evaluations across different scales and benchmarks. The SAMBA model was pre-trained with various parameter sizes ranging from 421M to 3.8B and evaluated on a wide range of benchmarks focusing on common sense reasoning, language understanding, truthfulness, and math and coding tasks. The performance of SAMBA was compared against strong baselines, including Llama, Mistral, Mamba, Gemma, Recurrent Gemma, Llama 3, and TFM++. SAMBA consistently outperformed all other models, demonstrating its superior performance in handling various language comprehension tasks. Additionally, the paper conducted experiments to explore different hybridization strategies, such as Mamba SWA MLP and Mamba MLP, to find the most efficient hitecture for language modeling with unlimited length extrapolation ability. The results showed that SAMBA achieved the best average score on all benchmarks, showcasing its effectiveness in combining the strengths of SSMs and attention-based models. Furthermore, the paper conducted rigorous and comprehensive analyses, including ablation studies and evaluations with up to 1.7 billion parameters, to validate the hitectural design of SAMBA and elucidate the mechanisms underlying its remarkable effectiveness.
What specific results were achieved with SAMBA in practical scenarios or simulations?
SAMBA achieved notable results in practical scenarios and simulations. Specifically, the largest 3.8B SAMBA model demonstrated superior performance in language modeling tasks, outperforming strong open-source language models with up to 8B parameters. SAMBA showed impressive results in various benchmarks such as MMLU, HumanEval, and GSM-8K. Additionally, SAMBA exhibited the ability to extrapolate to longer sequences, reaching up to 1M length in zero shot with improved perplexity on proof pile. SAMBA also excelled in memory recall tasks, being able to recall memories up to 256K context length with perfect memory recall in passkey retrieval. Furthermore, SAMBA showcased better performance on downstream long context summarization tasks compared to SWA-based models, while maintaining impressive performance on short context benchmarks. The hybrid hitecture of SAMBA was validated through rigorous analyses and ablation studies encompassing up to 1.7 billion parameters, highlighting its remarkable effectiveness in combining the strengths of SSMs and attention-based models for language modeling with unlimited length extrapolation ability.
What are the limitations or drawbacks of the SAMBA method according to the paper?
The limitations or drawbacks of the SAMBA method, as outlined in the paper, include the fact that the full attention-based models cannot extrapolate beyond their context length without specific length extrapolation techniques, which motivated the use of sliding window attention (SWA) in SAMBA. Additionally, the paper mentions that while SAMBA can achieve significantly better performance than SWA-based models on downstream long context summarization tasks, it still struggles with memory recall beyond a certain length. Another drawback highlighted is that the Mamba layers in SAMBA have slower training speed compared to MLP layers, leading to efficiency concerns. Furthermore, the paper discusses that the pure Mamba models may fall short on retrieval-intensive tasks such as squad due to their lack of precise memory retrieval ability. Lastly, the paper suggests that the existing zero-shot length extrapolation technique introduces significant inference latency overhead on the full attention counterpart, indicating a potential drawback in terms of efficiency.